regard. So, but first of all, let me briefly introduce where we are. So I'm at the University of Siegen since about, actually today is the 6th year that I'm there, exactly. And Siegen is located nearby Cologne and Frankfurt. So it's actually quite easy to reach by plane because you can directly fly to Frankfurt and then basically in 1.5 hours you are there. And so the place is a combination of, surrounding with a lot of universities and cities. This is North Rhine-Westphalia, which is the most populated region of Germany, but also a lot of green. So it's a nice place that combines research, teaching, and also beautiful landscapes, as you can see here in these pictures. And I'm part of the School of Science and Technology, in which we have 6 departments. And we are in the physics department, where we interact a lot also with the chemistry and biology, and also with the electrical engineering and computer science. So the scope of the School of Science and Technology is also to go more into interdisciplinary research. And diamond is certainly one of the things that can really bring up cross-cutting research activities. I'm also affiliated with the National Research Council. Actually, from today, I'm officially also with a part-time position in Italy. So the National Research Council is the largest research center in Italy, and I belong to the National Institute of Optics, which is an institute that exists since about 90 years, actually almost 100 years, and since about 20 years is part of the National Research Council. The headquarters are in Florence, but there are sections all over the country. And the activities are really focused on all the possible themes of optics and photonics. So we go from quantum optics and cold matter down to cultural heritage and the related themes. So now let me go to the topic of today's colloquium. And the first question is, why single photon sources, right? So why we need an object that is able to emit single photons on demand? So clearly, this type of device is strongly motivated by the rise of quantum technologies. Okay, so studies about single photon sources are going back to probably the 70s with trapped atoms, and gradually went into single molecules and then into solid state systems. But a real motivation for application, came up with the possibilities that are opened by quantum technology. So we are talking about, for example, quantum key distribution for secure communication, quantum cryptography as well. People are thinking about optical quantum computing using quantum states of light, quantum enhanced measurements in different ways based on color centers, but also based on complicated quantum states of light. And also, this is more like a classical area, but radiometry is also very important. So how you calibrate a detector using a deterministic source of single photons. So in this regard, there are different solutions. So historically, probably the technique that was started into this area of applications like quantum communication relies on attenuated lasers. So essentially, you take a laser and you make it as weak as possible, and statistically, then you can say that I can have a good chance of getting single photons. Unfortunately, this is not true, because the statistics of a laser is fundamentally different than the statistics of a single photon source. So it is always like an approximation. So then people came to heralded single photon sources, in which you use still a laser as a source, but then you use a so-called nonlinear process to generate a pair of photons. And then what you do, you use a single photon detector to herald the single photon, and then the other photon of the pair is free to move, and then you are sure that this other photon is a single photon. But of course, these are, you know, first of all, complicated approaches, and secondly, don't give the desired ultimate result, which is a deterministic single photon source on demand. So then that is why people started to look into quantum emitters, like quantum dots, color centers, and molecules. So of course, every emitter here has different properties, and someone is better in one respect, some other is better in the other respect, but are currently still all being strongly investigated. And here on the pictures on the right, you can see some concrete examples. So one is from Harvard University, from the group of Marco Lonkar, where they work on diamond color centers, and they use nanostructures like these pillars to enhance the emission of the single photon from the diamond color center. Or you see the two other pictures from CNRS in France, and also from Sparrow Quantum, which is a startup company in Denmark, where they use quantum dots in semiconductor, and they use photonic structures like micropillars or photonic crystals in order to enhance the emission properties. So in this respect, these two systems are probably the most advanced nowadays, and that's also the reason why they have already some startup companies. Also, CNRS in this regard has a startup company called Quandela. Okay, so the situation is very dynamic. As you see, there is a lot of fundamental research to be done, but there are also companies that are already, you know, selling some complete systems that generate single photons on demand. So what is the general problem here? I mean, the problem of quantum photonics, in which you want to play with single photons, is essentially boiling down to the manipulation and the generation of qubits. So a qubit is essentially the bit of quantum technology. So in a classical computer, you have 0 and 1. In quantum mechanics, you can have all possible combination of 0 and 1. This is based on the superposition principle of quantum states. So to make a technology out of this, then you basically need building blocks, and these building blocks are essentially stable qubits, which can be represented by matter qubits. So this could be our single photon source, for example, or could be another device that traps the single photon, like a single photon detector. And then, of course, these devices need to communicate with each other. And of course, the photon, which is also a quantum mechanical entity, is a very interesting system because it can travel without too much perturbation with the environment, because photons do not like to interact. And it can propagate, you know, with a very high speed, the speed of light. You can encode quantum information, and so on and so forth. So the problem is basically the interface between the photonic qubit and the matter qubit, right? The issue is light-matter interaction, which is very challenging because you have to basically couple a single photon with a single quantum system in matter. And so let's see a little bit maybe of basic quantum optics, because maybe this helps us to understand the differences and the challenges. I just made a few slides to sketch it. So light, as I said, is made of photons. And so these photons here are represented as a Hamiltonian, in which you have the operator associated with this photon. So A dagger A is the number of operator, and omega K is the frequency of the photon. And then you sum up all possible photon states. So the difference between a single photon state and a laser, for example, can be expressed using this quantum mechanical description, in which on the left, you see you have A dagger A times n equal n times n. So where n is a Fock state, so a state in which you have a well-defined number of photons. And on the other side, you have alpha, which is essentially a superposition of Fock states. And this is the laser state, which is not, as you see, a single photon, but it is a superposition of an infinite number of photon states. So that is the fundamental difference that motivates the research on a single photon source that can create a Fock state with n equal to 1. Then, as I say, the problem is light-matter interaction. So you need to interact these photon states with matter. And typically, this is described by an interaction Hamiltonian in which you have the photon operator, which are A and A dagger. And then you have the matter operator, which are sigma plus and sigma minus, which essentially represent the absorption and the emission of a single photon. And then you have this G, which is basically describing the coupling strength between light and matter. And so based on that, you can have two different situations. You have the weak coupling regime, which is essentially described by the spontaneous emission rate, which is the part that I highlighted with the red pen. And the other possibility is strong coupling, in which the quantum mechanical states of light and matter create hybrid states that are associated with both light and matter. And so in this talk, we will just talk about the weak coupling regime, which does not mean that the coupling is weak, actually. So be careful with that. So weak coupling doesn't mean that there is no efficient interaction. It just means that you are not dealing with the hybrid states of light and matter, but you are working in this kind of perturbation regime in which you can still consider photons as photons and matter as matter and couple them through this interaction Hamiltonian. And therefore, the result is that you have rates that are associated to the absorption, emission, and in this case, also spontaneous emission. Okay, so once you have the single photon, how can you be sure that this is a single photon, right? Because that is the problem. So imagine that you have your quantum dot, your color center, or a molecule in a certain sample, and then you want to know if this emits a single photon. So that's actually a quite fundamental problem, and this can be done by essentially measuring the photon statistics, essentially the correlation between the light, the photons that are emitted by your source. So here we need to discriminate between bunching and anti-bunching. And this is described in this sketch. So basically, what do? You take your source, you collect the light, and then you place a beam splitter before two detectors. So then your photon can be, with a certain probability, let's say 50-50, go either on detector 1 or on detector 2. So essentially, you measure the intensity at two positions with two detectors, and then you essentially do a kind of correlation function between these two intensities that you detect. So this is called Hamburg-Brown twist approach. And of course, this can tell you if your light is made of single photons. Actually, to be more correct, if your light is actually a single photon source. Why can you tell that? Because essentially, when you calculate this correlation function as a function of the time delay between the two detectors, if you have a single photon, you cannot detect at the same time this light on the two detectors, because either the single photon goes to detector 1 or it goes to detector 2. So basically, what you should expect is that there is a dip in the correlation function, which is this red line that you see in the sketch, when t, the time delay between the two detectors, is equal to 0. And so by this kind of interferometric approach, you can be sure that your source is a single photon source. If that is not the case, then you can have different possibilities like bunching. This is the case, for example, of the chaotic light that you get from your LEDs or illumination, or you can have essentially a flat response which is related to a laser, so a coherent states of light. So that's how we characterize a single photon source, and we will see a few times this anti-bunching effect later on. Then there is another important concept which is called indistinguishability. So, and this is related to quantum interference effect. So basically, now we know if our source emits a single photon using this Embry-Brown twist setup. But then the question is, these different photons that are emitted by my source are all identical or not? And this is actually an important question, right? Because if you go back to the slides where you have the matter qubit and the photonics qubit, and you want to make sure that these photonics qubit are essentially, corresponding to a certain quantum state that is in the matter qubit. And of course, if the system is not able to enforce this kind of coherence between the emission process and the photon, then you get difficulties in certain kind of quantum applications. So the quantum interference is another technique that essentially allows us to demonstrate if these photons that are emitted by the single photon source are all identical. And this kind of situation is shown in this sketch. So basically now you assume that you have two single photons, you don't have only one. And these two single photons emitted by the same source are then impinging on a beam splitter, and then the beam splitter can send the photon to one detector or to the other detector. So then you have four possibilities. The first is that the two photons go to the detector 1. The fourth possibility is that two photons go to the detector 2. And the second and third possibility is that each photon goes to the one detector. One time one photon, one time the other photon. And then if you do this quantum mechanical calculation, you realize that the amplitudes actually are positive and negative. So basically, the final result is that when you look at the situation where the photons have to arrive at the same time on both detectors, the probability that the two detectors click, so basically that the photons go at the same time in detector 1 and detector 2 is equal to 0. Because being identical, they have destructive interference at the beam splitter. So the only possibility is that the two photons go to detector 1 or the two photons go to the detector 2 at the same time. So this is actually a very exquisite quantum mechanical effect that you will not see using classical light. So that's why a single photon source that must be used for certain application has also to show quantum interference. So for example, the quantum dots that I described before are actually quite good also in the indistinguishability, and I already shown this quantum interference. In the quantum system that I discuss next, the color center in diamond, this is a bit more problematic. It has been shown actually at cryogenic temperatures, but not at room temperature. And the goal of our group is really to be able to play with this quantum mechanical effect at room temperature. And so I would like to show you next what kind of research activities we did in this respect. But before we do that, let me review a little bit the optical properties of solid-state systems, because we did not really talk about that, except naming a few systems. So of course, ideally, if you go back to the interaction Hamiltonian, you remember we have E and G, which represent the ground and the excited state of a two-level system. So this is the simplest situation of a matter qubit, in which light can be coupled to it and then when you absorb a photon, you go from the ground to the excited state, and when you emit a photon, you go vice versa from the excited to the ground state. So in this case, you have a spectrum for this photon, which is centered at the energy of the transition between the ground and the excited state. Unfortunately, this is not the case in a real system. So in the solid state, you have many different effects that you have to take into account. First of all, you have additional states in your system, so you don't have just a two-level system. And this is shown here in this sketch, where you see the absorption and emission spectrum of a single molecule. So you see that the spectrum has now different lines that are broader or narrower depending on the temperature. So the broad ones are at room temperature, and the narrow ones are at cryogenic temperature. So if we focus at low temperature, you see very well-defined lines in the emission spectrum. And these correspond essentially to the optical transition between two electronic states that involves also a change on the vibrational energy of the molecule, right? So this is, of course, a problem because you don't want to, waste energy into vibration, and this is, of course, has some limitations in the things that we want to do with single photons. In addition, if this molecule is sitting into a host matrix, then you have the host matrix that is also interacting a little bit with your molecule, and therefore it is possible that your optical transition couples some of the energy into the vibrations of the host matrix, which are called phonon. And therefore, on top of this sharp line that you see in the emission spectrum, you have the so-called phonon wings, which are another kind of loss mechanism or decoherence mechanism that take you away from the perfect or ideal two-level system. So if you now focus on the situation here of the phonon wing, you see that you have basically the nice spectrum of the two-level system, let's say. This is called the zero phonon line. And then on top of this, you have the phonon wing, which has a broad spectrum. And the strength of the phonon wing depends very much on the system that you have. So some emitters have a strong phonon wing, some emitters have a weak phonon wing. And this we will see later on in the case of color centers in diamond. But essentially, you have to pay attention to this effect that take you away from the ideal picture that you would like to have. So then let's talk about diamond, because this is basically the focus of this talk. So diamond is a material which is really exceptional. So it has the highest thermal conductivity of any material. It has a very low absorption coefficient in a very huge transparency window. It's very hard, it's the hardest material actually. It has chemical stability, and it is an insulator. So it's really unique. And people have already started to do, of course, devices based on diamond. In optics, you have lenses, diffractive elements. There are Raman lasers. People also do diamond electronics, like power electronics, LEDs a little bit less because it's a bit more difficult to get light out of it. And now recently people are working on quantum optical technologies. Probably you heard already of diamond magnetometers. And today we will talk more about single photon sources. So how to get a single photon out of diamond. So this requires that you create a color center in diamond. So essentially, a color center is a tiny defect that often is related to an impurity. So in this case, you see two situations. You have the nitrogen vacancy center and the silicon vacancy center. The nitrogen vacancy center is basically obtained by including a nitrogen atom and removing a carbon atom. So it's basically an atomic kind of system embedded into a solid state matrix. Similarly, you have the silicon vacancy center, in which now you place the silicon atom in between two missing carbon atoms. And this is because the silicon atom is larger than nitrogen, and therefore it cannot fit at the position of a carbon atom. And this small difference in placing the silicon and the nitrogen has a huge difference in the emission properties of these two systems. So how do you get this kind of emitter in diamond? Of course, you can have them naturally occurring, but this is not what we like to do, because you want to control these quantum systems. So typically what you do is that you have a artificial diamond sample that you create by chemical vapor deposition. So this is a standard fabrication technique that is applied to many different material systems and also to diamonds. So essentially you take a substrate. This substrate can be made of silicon, and then you get polycrystalline diamond on it because of the lattice mismatch. Or you can take a diamond sample that you create by high energy, high pressure techniques, and then you grow the CVD diamond, and this is single crystalline. With that, then you can incorporate these impurities in the grow process by, for example, injecting some gases containing nitrogen or silicon. Or that's what we do more. You take an accelerator and you implant these ions into the diamond crystal. So in this picture, you see like darker region, which corresponds to the region in which we implanted silicon ions. So the implantation process is damaging the diamond lattice, and that is why the transparency goes a little bit away, and you see this darker region. And to get rid of this problem, then what we do is to bring the diamond into a very high temperature furnace. We are talking about 1200 degrees for an hour, 2 hours or so. And then this will essentially do two things. Heal the lattice defects, so the diamond reacquires the transparency, and at the same time, it will give enough mobility to silicon ions and vacancies to find the configuration that you see here of the silicon vacancy center. So after this annealing process, basically, then you have your quantum emitter. And here is basically what you can get. You see in the picture of the two camera images, two different situations. So in the left panel, you have 10 ions per square micrometers. And in the second, you have 10 ions per micrometer square. So you can change the ion dose in the accelerator in order to implant more or less ions per area. And this is very important to determine whether you can get a single photon source or not. So typically, we need to go for 1 ion per square micrometer in order to be able to address a single photon. In this situation, then you can do the spectroscopy. And for example, you can look at the emission spectrum. And this is the panel at the bottom. You see at room temperature, you get a full width at half maximum of 1.6 nanometer, which shows the good quality of these color centers. And this is quite amazing because at room temperature, you get a very strong emission into 1 nanometer. And there are not many systems that have these features. Secondly, the spontaneous emission rate is relatively high. So you have typically a lifetime of 1 nanosecond, which is quite fast. So in principle, you could get like gigahertz emission from these kind of sources. So this will be really competitive with laser systems for single photon emission. And then, of course, the big question is whether these are single photons or not. And as I told you, then you go for this Henbury-Brown twist setup in pulsed excitation or in continuous wave excitation. And what you should expect is a dip when you have 0 time delay between the two detectors. And this is what we get. And this shows that we can have single photon emission from the silicon vacancy center. So then the next wish would be to be able to get these single photons under electrical excitation, right? So because this would be a real device. So this kind of problem has been addressed for the first time by Mizuoki et al. So a collaboration between Japan and Germany, in which way they took a nitrogen vacancy center in this case, and they placed that into a PIN structure made of diamond. So they created the P-type and N-type diamond by doping, like a semiconductor. This is very difficult, actually, and only a very few groups can do that. Probably the leaders are still in Japan. But anyhow, in this case, then you have a completely different process. So you see in the picture below the difference between photoluminescence and electroluminescence for the nitrogen vacancy. So in the panel A, you see the valence and the conduction band of diamond, and in this band gap, you place the energy states of your nitrogen vacancy or silicon vacancy, let's say. So you see that these states are actually very much resembling the two-level system that I described before. So you have the ground and excited state. So under optical pumping, you come with a photon, and this photon brings an electron to the excited state, and then you have the spontaneous emission, which generates a photon. And this is a single photon source. Now what we want to do is to use electron and holes that you deliver through the conduction and the valence band respectively. And so you have to be more careful. So what happens? You have the ground state of your nitrogen vacancy, and this ground state picks up a hole from the valence band, and then it becomes essentially a neutral state, because the charge state changes. Then what happens? You have that this hole has to essentially go to the excited state in order to emit a photon. So in the situation of holes, you know that the energy scale is opposite to the energy scale of electrons. So if you go up, you go to lose energy. If you go down, you acquire energy. So then what happens is that the holes actually in the capture process is not going to the ground state, but is going to the excited state. So then you go from a neutral state in the excited state that emits a photon. And then after emitting the photon, the center acquires an electron and goes back to the negative state that was in the original situation. So in this case, then you have emission for the neutral state of the nitrogen vacancy. And this has been experimentally observed. While optically, you can equally excite a neutral or negatively charged state. The same situation can take place for the silicon vacancy. So you see the cycle in the other panel when you go from silicon ground, silicon excited, and silicon ground neutral state. So the difference is that in this case, the state that emits a photon under electrical pumping is negatively charged. So therefore, the emission properties are different. And this very much depends on the energy level structure of the color center in the band gap of diamond. So I don't want to go much into the details because this would be a bit complicated, but is to tell you that the emission properties by optical pumping and the emission process by electrical pumping are very different, and they are not corresponding to the same emission spectra because of this charge state that can be active or inactive under electrical pumping. Anyhow, we made a theory which has been published in 2016 for this, and what is interesting for us at the end is the emission rate. And the emission rate, so how many photons you can get out of this color center by electrical pumping, can be approximated by this equation. So where you have phi, which is the quantum yield of the color center. So basically the probability that you get a photon when you go from the excited to the ground state. And then you have in the denominator of this equation 3 different contributions. So tau is the spontaneous emission. So this is the typical term that you have also by optical pumping. And then you have 2 other terms that are related to the capture process of an electron and the capture process of a hole. So Cn and Cp are the capture cross sections, and N and P are essentially the electron and the hole density that you can have in the conduction and in the valence band. So then to be able to get electroluminescence, you need to create electron and holes in the conduction and valence bands of diamond. So it means that you have to dope diamond, because we know that diamond is not conductive. So this is the first problem. The second problem, you have to make sure that this doping is effective, so that is not giving a small number of electron and holes. And this is also a big problem, because defects in diamond are basically trapping electron and holes. And then you have these capture cross sections, which of course depend on the quantum emitter that you have, because are also related to the levels of this of these emitters in the gap of diamond. So then there is a lot of technology to be done, and here you see some more theoretical results. So let's imagine that we are able to create a p-type and n-type diamond. So you have holes and electrons that travel, and at some point they meet a color center and they recombine to generate a photon. So based on this theory, you can estimate what will be the probability of emitting a photon, and therefore you can calculate the so-called emission rate, which is given in counts per second. So you see that the emission rate is strongly dependent on the current density that you have at the PIN diode. And the photon emission rate very much depend on the electron and hole capture process. So you see that, for example, the electron capture process appears to be the limiting factor, because you see that as you increase the current density, at some point, the emission process becomes quite flat until you go to such high current density that you activate other conduction processes, and therefore you get again enough electrons to provide holes and electrons for the recombination. Then, of course, it depends on the quantum yield of the quantum emitter. So you see here for the nitrogen vacancy, if you take 30% quantum yield, you get a curve. If you go to 5%, which we assume for the silicon vacancy, you get a lower emission. So overall, the emission rate is not very exciting, because you need to have a very high current density. We are talking about 100 amperes per square centimeter to get 10 to the 5 photons per second. However, we have to talk about the temperature. Temperature in diamond is very important, because if you increase the temperature, you are able to activate exponentially more and more electrons and holes. So by doing so, by increasing the temperature by just 50 or 100 degrees, you can have a considerable improvement in the emission rate, because you essentially provide more electron and holes. And here you see that the photon emission rate can really go up by many orders of magnitude if you increase the temperature by, let's say, 100 or 200 degrees. So eventually you can get to 10 to the 7, 10 to the 8 photons per second. And this is competitive to optical excitation. So this shows that if you want to do electroluminescence for single photon emission with diamond, you need to work not at cryogenic temperature, but you have to be able to work at higher temperature. And of course, this is a problem because we know that this will not give you a narrow emission line, which is required for example, photon indistinguishability. So nevertheless, this is still open research. And so we decided to also try that. And we went on by trying to generate the single photon into a conductive diamond sample. So instead of creating a PIN junction, we thought, okay, can we simplify these systems and get only, you know, one type of conductive sample? And we decided to go for N-top diamond, which is obtained by using phosphorus. And then here the problem starts. So you see here a diamond sample that has been implanted with different fluencies of silicon ions, 10 to the 14, 10 to the 13, 10 to the 12, and 10 to the 8. And you see that, unfortunately, in correspondence of the single silicon vacancy emission, you have also a huge background luminescence. And this is related, we found out, to the activation of nitrogen, which apparently is like co-doping diamond when you do the phosphorus implantation. But finally, we understood how to get rid of this problem. And in another sample, we managed to obtain single photon emission in a phosphorus doped diamond. So with this result, we demonstrated that it is possible to create a single photon source in essentially semiconductive diamond, which is quite important if you want to get devices for this type of applications. So we also investigated the single photon emission dynamics, which is based on the theory that I described before. And so in this case, we are calculating not the emission rate, but we are calculating the photon correlation that I described before in the Embry-Brown twist setup. So in this case, again, the process of bringing charges to the color center makes also the photon statistics quite different than under optical pumping. And this is because the correlation is also now dependent on these capture processes of electron and holes. And this can be clearly seen also in the experiments that have been done in Stuttgart on nitrogen vacancy center, and that we kind of interpreted correctly with this theory. So I mean, without going into the details, you can see that by changing the current density, you can really change not the nature of the single photon emission, but you can change really the G2 function from something that has a time constant of several nanoseconds to the typical time constant of optical excitation, which is of the order for the nitrogen vacancy of 10 nanoseconds. Okay, so this is about the activity on electroluminescence. Now I want to talk a little bit about one problem, which is the deterministic creation of color centers. So, of course, when you do the implantation, you don't know where your ions go. So, in principle, you create then a single photon source somewhere in your sample, and then you have to look for it with your microscope. So, this is certainly not ideal if you want to make devices. And so, we also investigated, like many other groups, how you can create this color center at the desired position with a kind of deterministic approach. So for what concerns nitrogen vacancy, this has been done by laser irradiation. So essentially you have a laser that hits a sample, and by hitting locally, you create the nitrogen vacancy. Unfortunately, this is not yet possible for the silicon vacancy. So some people use the focused ion beam to create localized implantation. On the other hand, the focused ion beam has a very low energy, so it gives you some additional limitation. In our case, we used much higher energies, so we have much more flexibility, and we adopted a pinhole, a 1 micrometer pinhole, in order to select the area in which we want to do the implantation. So you see a sketch of the setup. in which you get the silicon beam, then you have the pinhole, and then you hit the diamond sample under a translation stage, and then you create these patterns that you see on the top right. By changing the fluence, you get brighter or less brighter spots. And so the question was how to go to single emitters, and this took a lot of time because there are secondary ions that are scattered by the pinhole and so on and so forth. But eventually we went to this situation that you see in the bottom panel, in which you have these circles, and in this circle, sometimes we get a single emitter. So you cannot get a deterministic creation because the activation of the color center is still a stochastic process, but you can get a good probability of placing a single photon source in the desired position. Okay, so now I don't have so much time left because I promised to stay within 45 minutes. So let me accelerate a little bit here. So so far we talk about the diamond system and about the electronic properties. Now I want to talk about how you can improve the optical properties using a photonics approach. So one approach that we use is based on surface plasmon-polariton resonances. So you know that if you take metal nanoparticles, these have unique optical properties in the sense that have a surface plasmon resonance that is due to this coherent excitation of the electron cloud in the metal that gives rise to a broad resonance peak in the visible spectral range. And that has to do with the color that you see in this cup, that is a very old cup, which contains gold nanoparticles. So in principle, this is like a dipolar scatterer. And if you look at the dipole, you know that in the near field, the dipole has a huge electric field. And so we can think that this object can be used to enhance the emission properties of quantum emitters if you are able to place them in the near field, because the strong near field creates a kind of very strong density of photons. And as you know, in the spontaneous emission process, having a large density of photonic states improves the emission rate. So of course, we need to do it in a certain way, not just with a nanoparticle. And so here we created nanostructures based on gold, in which we use the shape of a cone, because you can get a very sharp tip and at the same time tune the resonance of the plasmon. And theoretically, you can get Purcell enhancement that are really more than 3 orders of magnitude. And we applied that to quantum dots, and we showed that we can have a change of the spontaneous emission rate by more than 3 orders of magnitude. This is shown here in these lifetime curves, where you essentially look at the exciton and bi-exciton recombination rate of a cadmium telluride quantum dot placed on an AFM tip. So the AFM tip is going close to the nanocone, and then when the coupling is strong, you get this very strong emission rate. But what we want to do is to really apply this to diamond color centers. And so here we also have some calculation which show enhancement of 4 orders of magnitudes. And currently we are trying to do the experiment. So this will be a concrete way to make emission extremely fast and therefore the source extremely bright. And another problem is about the collection. So these color centers are, first of all, dipoles. So you know that it's not easy to collect the light from a dipole. And secondly, diamond has a high refractive index. So the light likes to stay in diamond because of the total internal reflection that probably you studied when you went for, you know, the Snell's law in physics courses. So people have worked a lot in this direction. So people created solid immersion lenses, as you can see here, this picture from Imperial College, to get better emission from the color center. In other case, people work with nanoparticles. So here you see the example of a Yagi-Uda antenna created using gold nanorods. And this was applied to quantum dot, not to color centers. And another possibility is this planar structure that gets also a very high extraction efficiency, but unfortunately at high collection angles. So these are kind of problems that are still not completely solved, and therefore we went also for this and proposed this kind of structure in which you essentially have a planar Yagi-Uda antenna. So you have thin films made of metal that essentially work as a reflector and director to be able to create passive dipoles that are coupled to the active dipole, which is our quantum emitter. And due to the coherent coupling of these elements, you can strongly redistribute the radiation pattern. And let me show you the experiment because this is much easier to understand. So you see in the left column, the case of a molecule on glass. You see the emission pattern is very bad, actually. So you have the emission at very large angles. So these two-dimensional plots are essentially Fourier images of the emission, so basically the radiation pattern. So the circle is because your objective has a limited numerical aperture, okay? And if you start to take these thin films, you see how strongly the radiation pattern changes. And if you go to the double mirror situation, that is what we proposed as a planar antenna, you see that the emission now is completely focused in the central direction with a very small angle. So this is very interesting, and maybe let me skip this because it's a bit technical. And we try to apply this to color centers in diamonds. So we created diamond membranes because the planar antenna unfortunately requires a very thin active layer. And so we went down to membranes of the order of 100 nanometer, and then we applied this thin film, in this case silver, spaced by a certain distance, which is required in order to tune the radiation pattern. And this is the result of the experiment. So you have a radiation angle, which is essentially of the order of 8 degrees, half width at half maximum. And the experiment also show a very high directionality. So in principle, you can get also a very high degree of control on the emission properties. And let me just conclude with this slide on the roadmap that we published like a couple of years ago on nanoscale quantum optics, which is actually a much broader research area than what I discussed today, but is also very much related to the topics of this colloquium. So if you are interested to know more, you can freely download this roadmap. It is also now published into a review article in Rivista del Nuovo Cimento. And besides this roadmap, you can also look into some technological outlook, because we actually collaborated with a lot of companies when we made this roadmap, and eventually we made also market research study, which is also freely available on the website of this network. And yeah, this was presented 2 years ago at SPIE, and I think it got a relatively good resonance because it was one of the first studies on quantum technology. So with that, I'd like to conclude and thank you for your attention, and also thank my collaborators and the funding agencies that enable this research work. So thank you very much.
Thank you very much, Mario, for the nice talk. Very comprehensive overview and interesting results on the diamond technology and developments, recent developments. So are there any questions from the audience first?
There is a question in the chat box. I'm not so sure it's directed to me. So it's
maybe it's
from
to you. Can you read it out? Yeah.
Yes, it's from Matteo. So I think Matteo is somewhere here, but I can read your question, Matteo. So is it any manner to control the stochastic photon process emission, for example, by applying external field?
Yeah, of course, the photon emission is stochastic within the lifetime. So in a single photon source, you come with a pulse. The pulse excites your system, and within 1 nanosecond, you get your photon. So of course, you cannot control precisely the emission stochastic process, because otherwise you will not have a single photon. So if you had like stimulated emission, you could control that, but then you have stimulated emission, so you don't have any more a single photon, because you come with another photon to take the system into the ground state. So, but this is not a problem, in the sense that what is more problematic is for certain applications, not for all of them, is the indistinguishability, which is related to the additional dephasing that is introduced by the solid state system. So if you add an atom, the atom will emit by spontaneous emission stochastically, let's say within 1 nanosecond, 2 nanoseconds, whatever is the recombination rate. But if you take this into the solid state system, this rate is also affected by the environment, which is actually quite effective at room temperature. And this environment will essentially increase the decoherence of the system, and this will create essentially photons that are indistinguishable, not indistinguishable. And that's the problem. So the stochastic process itself of the spontaneous emission is not a problem.
Any other question?
Yeah, I have a question here.
Weibo.
Sorry, this is Weibo. So
Hi.
you showed your MV centers in your membrane. Can you remind me whether there is any transform limit emitters from the membrane based diamond?
Yeah. So this is this we did not really check, actually, because we don't go to cryogenic temperature. So to measure transform limited emission, you have to go typically with diamond at 10 Kelvin. And so we work only at room temperature in our lab. So that was like a decision because we wanted to not to cool down the system to get it better, but to accelerate the system to get it better. So if you now think about the coupling to nanostructures, and if you can make the emission very, very fast, then you can still get transform limited emission at room temperature. And this, of course, is very difficult.
If you really can get transform limited land within room temperature, that's
that's a bit our goal. So we are working on that. Yeah. It's very difficult, but diamond is probably one of the few cases in which you can go for it, because even at room temperature, the line width is still quite narrow. I mean, with a molecule or a quantum dot would be probably impossible because they would be too broad. But with diamond, I mean, it's challenging, but with 4 orders of magnitude improvement of the spontaneous emission rate, probably you can get close to that.
Okay, great. Good luck.
Thank
you.
If
you can get that, that's cool.
Yes.
Come back to tell us about it when.
exactly. So when we do it, you will hear it.
We will hear about it. Yeah. Any other questions from the students or the audience? So I have a general question about perspective for integration of the diamond. So first of all, I didn't know you could dope it P and N, and now I learned you can and make junctions out of it. So how people think about integrating with silicon photonics, either growing diamond on silicon to use waveguides or perhaps bond it or use visible waveguides.
Okay, so I mean, I say that you can get polycrystalline diamond if you grow it on silicon because of the lattice mismatch. So in this case, for certain applications, it's a bit problematic because you have a defect at the grain boundaries, and this creates background luminescence. So people in quantum technology are mostly working on single crystal diamond. and then it's of course a lot more difficult, because you grow it on a diamond substrate, and then you have to remove this substrate if you want to go for a device. And so you need some etching, and so in principle this would require a complete new platform based on diamond, so not CMOS or whatever. So one idea would be like a diamond platform. The refractive index of diamond is large enough to guide light, so one could do that. Actually, that's what people are doing. If you manage to go for a polycrystalline diamond, then you can also manage to integrate it with silicon. So actually, not in quantum photonics, but for example, in particle physics, the people have been working on diamond detectors for many years, and they are already able to bond diamond on silicon electronics to read out the detection. So this is done. People can bond diamond to silicon. So I think probably is even single crystal diamond, but we are talking about macroscopic things, right? So, but there is already a technology to bond diamond to silicon for electronics. Whether this is good enough for single photon, I don't know.
Mm-hmm. Okay. Any more questions from?
I have a question about, so you present the Hangul Mandel experiment at the beginning of your talk. So, so what is the status of this for this kind of system? So there is any chance to observe?
Yes, so the photon indistinguishability has been already demonstrated in diamond, single crystal diamond with a silicon vacancy at cryogenic temperature. So this has been demonstrated. The problem is that if you take diamond color centers at cryogenic temperature, you cannot compete yet with quantum dots. Because if you take the quantum dots of, the group of Pascal Senelart or Lodal in Copenhagen, I mean, they are still much better than the color centers. So in my opinion, the big advantage of the diamond is that could be potentially integrated into a platform, and maybe also brought to room temperatures. So if you could manage to bring it to room temperature, this would be, of course, a revolution. Because with the quantum dots, it's not completely, I mean, it's not doable, because these quantum dots at room temperature will basically be so bad that there is nothing that you can do to get the right source. So.
Okay. Last chance to ask questions before we dismiss the audience for Easter break. No?
Okay.
All right. So
maybe you find a diamond in your chocolate egg.
Yeah, maybe. And then we bring it to the lab and implant it right away.
Exactly. So you don't give it to your wife, but you use it for research.
Yeah. Okay, so Mario, thank you very much. It was a very interesting talk, and we hope you will be able to come in person soon. And,
yes, I hope so.
Yeah, we do, there's several groups, Weibo, you probably know, and,
yes.
Other people here that work with, now we start working with implantation as well with focused ion beam. So there's certainly several synergies that we could exploit.
Yeah.
Right, thank you very much for attending the talk, and thank you, Mario, again for delivering it, and see you next time.
Yes. Happy Easter. Thank you.
Happy Easter.
Thank
Bye-bye.
you.
Ciao.
Bye-bye.
Bye.
Bye-bye.